Okay, so enthalpy, so a definition for enthalpy. Enthalpy basically is delta H. Remember that H means change in, but we will not often use the final minus initial, okay? We will in some cases, but that's like later on in this piece of the unit. So for now, you can almost ignore the delta, but technically it has to be there to be enthalpy. So enthalpy is same thing as Q, okay? And we're going to talk about enthalpy at constant pressure and or enthalpy when we have the difference of heat that's made, that's transferred between reactants forming and, products forming and reactants breaking. Okay, so nothing to write down on that slide. This screen just reminds you, or this slide just reminds you about enthalpy for an exothermic reaction, right? We're going to look at these energy diagrams later on in this unit and be able to do some things with them, but very simply. We won't look at quantitative data too much, mostly just the qualitative of what it looks like. So an exothermic reaction, if you remember, a while back I said pretend like this is a high-rise building, right? And the door's right here. That's my door. That's a horrible door. We'll pretend it looks like a fantastic door. Okay, and an exothermic is when you're going out the exit door, right? So your product line is coming out the door. Endothermic, your product line is higher. Okay, so when we have an exothermic reaction, remember that's going to feel warm to the touch or warmer to the touch. When we have an exothermic reaction, delta H is going to be negative, just like Q. When we have an endothermic reaction, delta H will be positive. Okay, so Q and H really aren't really different, really that much different. Really, we deal with delta H when we're talking about a chemical equation, and Q is often used with the chemical equation, but also can be used to look at transfers of heat like we did when we heated up the metal and put them in water and whatnot. Okay, this is just sort of a summary page, right? Talking about endo and exo, right? Nothing to write down on here at the bottom of page 10, just reminding you what endo and exo mean and the different terminologies that we've used. And so let's look at this first problem together. Okay, so the first thing we have to do is we have to have a balanced equation to do this, okay? So that's where the chemistry is coming in again, right? And it says when 1 mole of methane is burned at constant pressure, most of the time, if not all the time, I'm going to give you the balanced equations because I just need that not to be an issue for you. So our balanced equation, because it's undergoing combustion, would be this, or our equation. And I will either give you the equation and have you balance, or I will give it to you and then you'll have to balance. So please write that CH4, that's methane, burns, that means plus oxygen, and it makes CO2 and water. So we do a combustion here. I have 1 carbon and 1 carbon. I have 4 hydrogens, so I got to put a 2 in front of water to get 4 hydrogens, pardon me. So 4 hydrogens on the left, put a 2 in front of H2O, now I have 4 hydrogens on the right. I have 2 oxygens on the left, and I have 4 oxygens, 2 here, because there's a 1 here, remember. 2 there and 2 there, so that's 4, so I got to put a 2 here. So this is balanced with a 1, 2, 1, 2. All right, so first we have to have a balanced equation to do these, and then it's very important that we think about what it's saying is the in and out, like before, right? So we know this much energy is released, right? Let me get to change colors here. So we know this much energy is released, right? And then released is important. And we know that this is our out. Okay, not the, let me do this. This is our out, right? And the amount in, what made that amount out is our 1 mole. So this is our in. So our 1 mole is our in, our 890 is our out. Now, when I say out, I want you to be careful with my terminology. I don't mean out that it has to be negative. I just mean heat is transferred. So the result. In versus out. So I put this much in and I either absorb so much heat and it's positive, so it's absorbed, or I release so much heat and it's negative. Okay, so let me clean that up a little bit. And we can think about the fact, and you could write this down over to the side if you want, but our in then, I gotta switch back to my pen, hold on. I wish it was just a click of a button. So our in is gonna be 1 mole, right? And our out is going to be 890 kilojoules. Questions about that piece? Now, 890 kilojoules, but I wrote a kilojoule, right? So anytime I write a calorie, a joule, or a kilojoule, I got to consider its sign, right? Its direction, and it's negative because I see the word released. Questions about the in and out piece first. Okay. So then it says calculate. So all that is just the information we need. That's our relationship. This is my relationship, right? If this would have said 15 moles, I would have put 15 to that, right? And it would have been 15 at negative 890 or 890 to 15. It wants to know now what is H when you have 5 grams of methane. So we're going to start with 5 grams of methane. So 5.8 grams of CH4, that's methane. Now, how do we get rid of grams of anything? Well, we periodic table number, right? So we're going to take the periodic table of methane, so 1 carbon and 4 hydrogen, 16.05 grams of CH4. We know the periodic table number is always equal to 1 mole of CH4. And why do we do this? Because I can't use this relationship, right? My in versus out relationship until I get to mole. And I know from the word problem that 1 mole equals negative 890 kilojoules. And you can put the formulas there if you want. But with this lesson, we'll never be doing 2 different kinds of chemicals. It'll always be about the same chemical with this lesson. Okay, questions about how I set that grid up? See, our in versus out relationship is right here, right? And units canceled. In-out relationship is right there, and we canceled units, didn't we? So we're going to multiply across the top. Oh, I don't know where my calculator is. Okay, so we're going to multiply across the top. So 5.8 times 890 negative, divide by 16.05, and we get negative 321.12. Oh, that's not the right number. Well, I'm trying to write on my board here. Negative 321 point, let me try to read that number better, 62 kilojoules. Technically, or kilojoules. With me? Questions for clarity on that? All right, let's go on to 13. Look at that, I typed that all up. I should have showed you that one. That
Yes, I do have a question.
Okay, go ahead, sorry.
So what's the formula for this problem?
There isn't a formula for it. We're using a grid. And that's because we already knew, and this is the same problem, we already know how much kilojoules we have based on 1 mole. So now we're showing the relationship that thermochemistry has. We would have already somehow, okay, to answer that question, that was already done for us. We did Q equals MC delta T already and got this much kilojoules. Okay, so that was done ahead of time. Questions about that? Other questions of clarity? All right, so let's look at this next one. We have a balanced equation, and look what we have this time. This time they gave us the thing. So guess what? This is so fun. I'm so excited to show you this. Ready? I can make a relationship between any of these 3 and that. What do I mean by that? 4 moles of iron to negative 1652 kilojoules, or 3 moles of oxygen to negative 1650 kilojoules, or 2 moles of iron oxide to 16. So those are all relationships that can be set as ratios. Okay, so we're going to start with what we're given. We're given 6 moles, if I can get my pen to, oh, let me try to turn it right side up. 6.00 moles of iron. Everybody with me? How did I get that? I got that from right here. This other stuff is just garbage, right? We don't care about it. We're looking for the number and the unit in the formula that we are given. Okay, so then we can say, well, I have to have moles of Fe here, don't I, to cancel. And I know from my balanced equation, I have 4 moles of Fe for every 1652 kilojoules. Now, I want to talk about the negative piece separately, so I didn't put it in right now. But first, I want to see that, do you see there's a relationship between each of these coefficients, the moles, and the value of delta H? I can set them each as their own ratio. Now, when do you use the negative? Well, that depends. So as this is written, going this direction, there is a negative with the delta H. If I were to decompose iron oxide in the same conditions, we would assume that the sign would flip to positive because it's the opposite direction of the reaction. Okay? So going forward, this is an exothermic reaction. So the synthesis of iron 3 oxide is an exothermic reaction because this is negative. If I reversed it, it would be positive. So if I went and made iron oxide break down into iron and oxygen, the opposite direction, going this direction from right to left, I would assume this sign would flip. So knowing what the sign is in this relationship depends on how the word problem is written. That's the part that sucks. Okay? So here's what you do. You look at the wording of the problem. It says iron is reacted with oxygen. Do you see that? Iron reacted with oxygen. Does the reaction as it's written, assuming that it's written forward like it is, does it show iron reacting with oxygen? And you see, yes, it does. So therefore the sign would be negative because the way it's presented is also the way it's asked about. Okay, it says iron reacting with oxygen. This is showing iron reacting with oxygen. When iron reacts with oxygen, our delta H is negative. So we'd want to have it be negative down here. And we're going to practice several of these and you'll start to get the feel of it. So we're going to take 6 times 1652 negative and divide by 4. And you get negative 2478 kilojoules. So no formula again, because all that has been done for us with the skills we've already learned. Okay? And we already have the delta H/Q. All right, I think there's A through F of these or something like that. So we're going to keep going. Questions before I go on. And I can't see everybody's face because I have my presentation in me questions, so you'll have to unmic if you need clarity. Okay, let's look at 13B. Okay, 13B. So we're looking at the problem. We're looking at mole of iron oxide is produced. So we're going to start with 100 mole of Fe2O3. Okay. And we know from our balanced equation, 2 moles of Fe2O3, so it cancels, equals 1652 kilojoules. Now we're going to decide if this stays negative or flips positive. Let's look at the wording of the question. Does this reaction, the way it's written, show iron oxide being produced? Shake your heads yes or no. Does this reaction show iron oxide being produced? It shows iron oxide being produced. This is the produced side, right? The way this is written, it shows iron oxide being made or produced. So therefore it's forward, meaning it's written as is, and it would stay negative. Questions about that? Clarity for that piece. That piece is important. So 1652 negative divide by 2, and we get negative 826 for our answer. Kilojoules. So the sign stayed like it was because as it is written and as it is requested is in the same order. Give me just a second. I want to check something in the assignment before. Okay, questions about that one? That was a negative 826. All right, let's look at 13C. All right, so we're going to start with the only number given to start with, 1 gram of Fe. Now to use the balanced equation, I got to get moles. So I got to say, okay, I know there are 5585 from the periodic table grams of Fe for every 1 mole. Remember, periodic table number is always per 1 mole. Pardon me, why am I doing this? Because I got to get moles to use my balanced equation. Then I know 4 moles of Fe equals 1652 kilojoules. Now we got to think about the sign, and we're going to do that in just a moment. We know it always equals the answer of delta H. We just have to figure out whether the sign is staying as is or gets flipped. Does this reaction show iron reacted with excess oxygen? Don't worry about the word excess. Does it show iron reacting with oxygen as it's written? It does. So therefore it stays negative because it says negative when it's written that direction. So 1 times 1652 hit equals, negative 1652, apologize. Divide by 5585 hit equals, or you can do it all at once, divide by 4. So you can do the math however's best for you. I don't like what my calculator just did. I hit something weird. So let me try that again. 1 times 1652 negative. I don't like to put parentheses in, so I hit equals every time before I divide. But you can do it how you want. Okay, so negative 7.39 kilojoules. Questions about C? Okay, let's look at D. This time we have two things. It says how much heat is released when 10 grams of iron or 2 grams of oxygen are reacted. Well, we don't know the excess reactant. Notice last time I told you that, right? So we got to do two grids. We're going to take 10 grams of Fe, and we're going to take 2.00 grams of O2. And we're going to figure out how much kilojoules that's going to release in those circumstances. So 5585 grams of Fe, periodic table number for every 1 mole of Fe. And we know that we're going to have 4 moles of Fe from our balanced equation for every 1652 kilojoules. Now, is it negative or positive? I got to go back up here, and it says they're reacted, so it's forward. So it stays as is because it's negative because it's showing iron reacting with oxygen in that balanced equation. Now, careful on oxygen. Remember, that's going to be 32.00 grams because I have 2 oxygens, right? 16 twice. For every 1 mole of O2. Okay, the 32 is because I take 2 oxygens. Got to write the molar mass, the periodic table number based on what I have in front of me. And then here we have 3 moles of O2. Why? Because there's a 3 in front of O2 up here. And it's going to be negative 1652 again. Because again, it's saying that iron is reacting with oxygen. That's what it's saying delta H would be. Negative 1652 if iron reacts with oxygen. All right. This is a limiting reactant problem, but we don't have to do all that hard stuff we did before. This is a little bit simpler. I'm just going through the math and multiplying across the top, dividing by numbers on the bottom. Here we get negative 73.9 kilojoules. Okay. And here I get negative 34.4 kilojoules. Now, questions about the math before I talk about how we picked the right answer, because this is a little funky. All right, it said the least amount. Now, they're negatives, but the negatives only indicate direction. They're not really negative numbers, right? It's not like negative 2, negative 1, 0, right? So we still pick the smallest value, even though technically in the world of numbers, negative 73 is smaller than negative 34, right? But because the negatives don't matter for the number, they only help us understand direction, meaning in both cases heat was released, the correct answer will be the 34 number. That's the least amount of heat that would be produced if we reacted 10 grams of iron and 2 grams of oxygen. I could never get to the 73 because all my oxygen would be gone by then. So you're going to pick the smaller number even though they're negative values. Remember, the negative only tells us direction. The number tells us amount. Questions about D? All right, let's look at E. No questions yet? Okay, so what do we have? We're given a number of 566. You're going to find these to be a little bit easier once you get working on them. Fe2O3. Okay. All right, so we're going to say there's 2 moles. We don't even have to worry about the periodic table because we already have moles for every 1652. I'm not going to put the negative in yet. We got to evaluate whether we need it. 1652 kilojoules. 2 because there's a 2 in front of Fe2O3, and 1652 because that's the delta H value given. Now, looking at the wording of the problem, it says Fe2O3 decomposes. Decomposes means breaks down. Does the reaction with the delta H as a negative show iron oxide breaking down? Or would we have to reverse? We would have to reverse. Does everybody see that? So that means we're going to put a positive 1652 in here. Positive 1652. Because the reverse reaction we would assume would give us a positive. Now we're just going to calculate the math. So 5.66 times 1652 divide by 2 gives me positive 4675.16 kilojoules. Okay, is everybody clear why it's positive? Because the reaction that's given as a negative is not the same direction that the question is asking about. Okay, you try F for me. You try F. When you get a moment, you're going to try to get the answer that's on the screen for F. Check your answer when you get... Okay, so then I'd like you to write these two answers down for 14 and try them for your homework tonight. Try 14 on your own, please, and let me know, email me if you're struggling. And then after you get that written down, you are dismissed, and I will check in with you all on Monday. Please work on any missing assignments. I've only kept you in this Google Meet for 21 minutes, so you still owe me technically 26 minutes or whatever. So please, please, please work on your missing assignments.